Lecture 9, set 5, handshaking. We just saw an example in the previous set when we had a result R, which was basically the sum of the square root of P and square root of Q. And the way we solved it was by designing one square root function, and then we had a simple control finite state machine, which in which one clock cycle called the square root and computed the square root of P. The next cycle it computed the square root of Q, and basically just stored these values and added them in the registers to get the final value. So basically the same this is going off the board. Same function was used twice, but kind of time multiplexing, so it was not, we didn't have two instances of the same module. The same instance was used, and we just passed, the variables through the same hardware. Now, what if things get a little bit more complicated? What if, I have a design where each of these square roots take more than one clock cycle? What if I have a design where the module that I'm trying to use and pass variable on is being used by someone else, and then I have to wait till it finishes what it was operating on. To address this case, the protocol that we use to address these case, so for more complex designs where we are reusing the same module, what we do is we are using a protocol called handshaking protocol. And handshaking is pretty simple. Usually the top level or the master program that is calling the other one is called the master, and then the slave is the one that we call the variables to. In this particular case that we had, the master was trying to have the value R, and then it was calling the square root twice as the slave module to do these operations for it. Now, what happens is that, the slave is, of course, in some idle state. And then the master wants to start the operation. So what it's going to do is it's going to send a signal start to the slave. I mean, this is of course, the most basic case I'm covering. I'm going to cover a little bit more complicated scenarios as we go on. But like in the most simplest case, let's assume that the master is going to tell slave, hey, start the operation. And what the slave, and it's going to send also the inputs to the slave. And now if slave is taking multiple cycles, so basically here what happens is that it's going to have a start and send inputs, and then this is going to do some operations, and we don't know how many cycles maybe the slave is taking to do the operation. Maybe the number of cycles is dependent on the values or the parameters that I'm passing, and it may not be known in advance. So then what happens is that I'm going to have designed some handshaking protocol. In the simple protocol that I'm doing now, let's assume that the master has this probe which keeps probing the slave, asking, are you done? And then, this could be taking some cycles. Again, are you done? No. And then at some point, I'm going to ask, are you done? And the slave is going to say, yes, I'm done. And once this happens, what the output is going to be red because this is a valid output. And then this is again going back to idle state. So if I want to show it on this diagram, after it's the slave is done, it's going to tell the master that the output is ready, and then that it will have the data out to the master. Let's see how handshaking works in practice when we do the code, and how this actually impacts how handshaking can be a little bit twisted to have more variables, like, for example, if multiple people are calling the same slave, so on and so forth. Let's go through an example of this and see how that actually works in practice for the code that we just saw. We showed this kind of more complex code in the previous set. And as I mentioned there, the details of this code are not important. What is important is that we are having this a little bit more complex code that we were calling the same module twice and passing parameters and saving parameters. Last time we just did it in a using just a clock in 2 states, and now we want to design this system where we have added handshaking signals to the master and slave. In this particular case, the slave is the square root function. The master is kind of the top level design that calls the slave function. And now, as you see here, the slave function, which is the square root, has these interfaces. It has as input start and data in, and as output signal it has ready and data out. So when we declare the slave, we need to declare these signals and make sure that we have them on board. So this is basically the declaration of the slave. It's similar to the one we've seen earlier, and again, the inputs, the details are not important. But the handshaking signal, as you see here, it has the input has the clock and reset, which we always have, but it also has the start and ready as they which are added to the regular list of inputs and outputs for the module. And these are used explicitly for handshaking. And then because we had that, if you remember from the previous what I wrote on the board, we had the master slave, and then we had the ready and start, and then we had the ready, the start was going in, the ready was going out, and then the data was coming out, and then we had some data in as well. So now what happens here is, we need to design that finite state machine that says, are you ready, are you ready, are you ready? So there are these 3-4 different states that we had in the design that we had. Here, if you remember, we have the start state where we also send the input, then we have the wait state, and then we have this ready state where the output is ready. So in addition to the idle state that we originally had, we have these 3 states, and if we are designing a master slave, we need to define these 3 states in the code. So as we are doing the slave, we need to do sequential logic or a finite state machine that controls this. So what it says is that if you are in the idle state, if the ready signal comes, we are basically, it basically means that you reset the values to 0. But if the start comes, then we go to the begin. So we go to the state 1, and the state 1 is that state where you do the operation, but the wait state is is just going to be saying that this output is not ready. So the master would know that this is a wait state. And once this is value is computed, then it's going to say that the ready is 1, and then it's going to go to the idle state again. Exactly like that chart that we were showing in the beginning of the road. So basically, if the start, this is going to go to the state 1, and other than that, it's going to get the things ready. And the handshaking is going to have the similar handshaking signals have to be, or corresponding handshaking signals have to be also implemented on the master side. So master, remember the master had this